Okay, so we are discussing canonical ensemble. And in the previous class, we discussed application of canonical ensemble to ideal gas, and we have also discussed if you have, for example, ultra-relativistic ideal gas, it's very easy for you to solve this problem. I also showed you that it is not that easy if you want to do it using microcanonical ensemble. Okay, so we have the following things that we have to keep in mind. So I will try to write these things every day so that you don't forget. So we have a canonical ensemble. That means you have a set of microstates, and each microstate can differ in its energy. That is, energy is fluctuating. So this corresponds to, so you can ask a question, what is the probability of a microstate? A probability of a microstate with the energy EI. This is given by 1 over Z into e to the power minus beta EI. This is called the probability of a microstate of a system with energy EI now here the system is in thermal equilibrium with a heat bath at temperature E, where this beta is written as 1 over AB. Now this Z, which is obtained by demanding that the total probability should be equal to 1, is sum over I e to the minus beta here. Now you can see that this is called canonical probability, canonical partition function. Now you can ask a question that this Z depends on what? What properties? Suppose if you ask this question, the answer is this Z depends on on macro state. Essentially, the macro state is defined by P, V, and N. So Z is a function of P, V, and N, or equivalently we write it as Z is a function of beta, V, and N, because beta is just inverse temperature in units of K. Now, if you see that beta is appearing here, so Z is a function of beta is understandable. EI is there, but EI is summed over. And how many microstates are there? That information is contains this N, and then this EI in general will depend on the volume, and that is how you get a volume dependence in the into this jet. Okay, so note that that the dependence enters enters to Z through EI. Okay, to understand this, let's say if you have, for example, if you take consider particle in a box. Okay, now for particle in a box, the energy EI is equal to h bar square I square divided by twice m L square. Okay, let's assume this box is like a cubic box. Okay, so assume a cubic box. Now this I square, maybe you can write it as ix square plus iy square plus iz square. Okay, but that's not very important for me. Okay, so this is, let's say, h bar square I square into, let's say, some ix square plus iy square plus iz square, because this ix, iy, iz are like quantum numbers associated with each one of these directions. But I want to write this as v to the power 2 by 3. So you can notice here that this EI actually is a function of volume. So the volume dependence to the partition function comes through the energy values. Okay, so now I think it is clear that the canonical partition function is a function of the macro state, that the temperature through beta and volume and number of particles. And we have seen connections to thermodynamics. Connections to thermodynamics. We have established 3 to 4 connections. So the first connection is the Helmholtz free energy, which is a function of, again, TV and N, will be equal to minus KBT logarithm of Z, which is a function of TVN. Okay, so this connection you can use to go from statistical mechanics to thermodynamics. The second connection that we have shown yesterday is U can be written as the average energy of the system as minus del by del beta of logarithm of Z. So this is another connection that we have made to relate a thermodynamic quantity from the partition function. And the third connection we have written in terms of the entropy, which is minus Kb sum over I, Pi logarithm of Pi. This is what, so where Pi is canonical probability density, Pi is equal to 1 over Z into e to the minus beta Ei, where Ei is the energy of the ith microstate. And the connection that we have made with respect to fluctuations in energy, namely the average E square minus average E the square is equal to KBT square into CV, where CV is the specific heat at constant volume. So these connections to thermodynamics have been made, and we have to use these connections to relate our calculations to thermodynamics. So I think whatever I have written so far, that is up to this, and starting from the beginning, this is like a capsule which you have to always, I do not know, understand or memorize or mug up, whatever you want to do. But if you want to use statistical mechanics and make progress with statistical mechanics, this much is the minimum information that I expect every one of you should remember, or it should be at the tips, so that you don't have to look for anything, uh, anything more than this. Okay. So that is one important point. And as we have been discussing earlier, so I am trying to do this canonical ensemble in two different tracks. Track one is I'm trying to discuss some general aspects of ensemble. So this, for example, all these are general aspects. Okay, so these are relation. General aspects means I'm not considering any system. There is no application. That means the results that we are deriving under general category are applicable for canonical ensemble, whatever is the system. The second track is where we are trying to do applications, like we try to do ideal gas, we try to do ultra relativistic ideal gas, and so on. So today I will once again try to do a couple of general results. So this is under the track one. So general results. Okay, so we have already shown that a canonical probability distribution is given by this kind of a form. Now we will try to get some insight into this idea. So for that, let's say that I have a canonical ensemble. And let's say in this canonical ensemble, let's say that it has some n microstates. Okay, so please differentiate. This is a script n that I am writing. Why I am writing like this? Because the n I am already using for the number of particles. So I want to distinguish this number of particles from the number of microstates. So let me put it in this way. Maybe you can ask me, why are you not using the omega, which you are using already in microcanonical ensemble? But I want to make sure that this is not same omega, because this number of microstates are much larger than omega. So let me just use this n. Yes, this is the, it has totally this many number of microstates. But now you know that the canonical ensemble now can be partitioned in terms of different energies. Okay, so that means let's say you have energy E1 and energy E2, energy E3, etc. There are different energies, and associated with this energy E1, let's say I have N1 number of microstates, and I have N2 number of microstates, and I have N3 number of microstates, and so on, such that so these are essentially distinct energies, and these are uh, number of microstates microstates of respective energy. Okay, so now as you can see that this is actually fixed. This is fixed. The number of energies are fixed once you have a canonical ensemble. Now this, once you know that there is some kind of a nj, that means the set n1, n2, n3, etc., etc. This is your set n1, n2, etc. There can be infinitely many energies, so this can be infinite set. So I'm going to denote this set by a curly bracket like this, and this particular uh, numbers, we'll call it as a mode. A mode. Okay, this is one mode. Now, once you fix your mode, there are different ways in which they can arrange themselves. Okay, so that means once your mode is fixed, it's not that there is only one way in which this can happen. But before that, let me also tell you that this particular arrangement follows these equations. That is, if you can write down sum over j nj, that means all possible energies, if you sum, then it has to be equal to this total number of microstates. This is obvious. And suppose if I write down sum over nj into ej, suppose if I write like this, then this corresponds to, remember, each microstate is the whole system. So you have uh, that means you are actually taking so many times the same energy. So if you can write down this average energy of the system as internal energy, so this quantity will be n times here. Course, we mean that U to be the average energy of the system. So these are like these are the constraints constraints a mode should obey. So these constraints have to be obeyed. Now let us come back and then say that a mode defined as this nj can be realized in many ways. A mode can be realized in many ways. Okay, so we can ask a question, how many number of ways that a mode can be realized? So if you can define this as W of Nj is the number of ways in which you can realize this mode, and this is, that means you have a total script n number of microstates. Among them you have to group them in terms of this without bothering about the ordering of this. So this is essentially a generalization of uh, what we discussed. Instead of a binomial coefficient, this is called a multinomial coefficient. That is factorial n1, factorial n2, etc. Or I can write this in a shorthand notation like this: factorial n divided by product over j nj factorial. Okay, so this is, instead of sum over, we have to write this as a product over j. Okay, so this is the number of ways in which a mode can be realized. Now you can ask a question that uh, the probability of a particular mode is actually proportional to this number. Okay, so recognize that probability of a mode is proportional to the number of ways in which that mode can be realized. So now you can ask a question that what is the equilibrium mode? Which mode is what is the equilibrium distribution of these microstates? And that is given by a particular mode for which this W of Nj is maximum. So we can obtain um, so let Nj star be an equilibrium mode. Which is also the most probable mode. So we can obtain this Nj star by maximizing this W of Nj subject to the constraints given. So let us call this as equation 1 if you want, given in equation. So you have to maximize these constraints, subjected to the constraints. So maximize this number of ways in which you can have this mode be selected, mode to be realized, subjected to those constraints. Now, this kind of a maximization is, I do not know if you have come across this earlier. There is a technique, I am sure you might have seen this technique when you did it at least classical mechanics. So there is a mathematical technique called uh, constrained extremization. Constrained extremization. So let me just introduce this technique to be on safer side, so that some of you may know, some of you may not know. So the problem of constrained extremization is something like this. So let us do this in steps. Suppose if you have a function of x and you want to extremize this function. Okay, so extremize this function of x implies, what do? You ask the question, what is dou f by dou x is equal to 0, and this gives you x is equal to x star, which is the point at which this function is extreme, the maximum or the minimum. Okay, so this is a function with respect to one variable. Now, suppose if you have a function of several variables, suppose you have a function of x1, x2, etc. Let's say you have xn. Now you want to extremize this function. So that means if, let's say, x1 star, x2 star, etc., xn star is a point at which f is extremum, that implies that your del f by del xi is equal to 0 for all I is equal to 1, 2. Essentially, this is like gradient of f. Okay, so this is same as writing this gradient of f is equal to. So you get a set of n equations here, and by solving those n linear equations, you find out the coefficient. You find out the point at which the system is the function is extreme. Now, so now let us say that we have a third case where we want to extremize this function, extremize a function of several variables, let's say x1, x2, comma xn. Now I want to extremize this subject to a constraint, and usually constraint is given as an equation. So there is some other function given g of x1 of xn is equal to 0. So this is the constraint equation. So I want to extremize this function subject to a constraint like this. This is something like this. So imagine that you have got some kind of a hill like this, and you want a point where the maximum is. Then that point corresponds to this value, right? This is the point at which maximum is. Okay, but suppose on the other hand, let's say that you are not doing trekking, you are not climbing this hill, but you are taking your car or motorcycle or something like that, which means there should be a road. Okay, so let's say there is a road like this. Okay, so a road like this, and probably this is the point, maximum point which you can reach by road. Okay, so by road, because after that there is no road, so you cannot go in your car. So this road is your constraint. So if you want to find what is the maximum point by road you can reach, then this point is not same as this point. This point is something different. So this is the point. So this is how the extremum point of a function with respect to a constraint will be different from the extremum point without a constraint. So this is just an example. So we would like to understand how to find this extremum point. So you know that uh, I want to find the extremum of f. That means I must say that extremize f implies the variation df should be equal to 0. Now we can write down this df as sum over I is equal to 1 to n del f by del xi into dxi is equal to 0. Now, if there is no constraint, if there is no constraints, then all these incremental variations is set are linearly independent. And because they are linearly independent, this implies that del f by del xi is equal to 0 for all I is equal to 1 to n. So this is what we said in case 2. Okay, so case 2 here. In this case, we said if there is no constraint, then dou f by dou xi is equal to 0 for all I. Now, what happens if there is a constraint? If there is a constraint that this all these dxi are not linearly independent. Okay, which is so if there is a constraint, not all dxi are linearly. So we will not be able to write this equation that all dou f by dou xi is equal to 0 for all. Now our aim is to find out what kind of equation should we write in this particular. Now the constraint equation is given by g of x1, x2, etc. xn is equal to 0. Since this is a geometrical constraint in this configuration space, we can write down dg is equal to 0. Okay, so which implies I can now write down sum over I is equal to 1 to n del g by del xi into dxi is equal to 0. A similar equation like what we have written here can be written. Now, since we realized that there is a constraint, which means constraint can be actually used to reduce the number of independent variables, and hence I can think of using this constraint equation to write one of the dxi's in terms of all others. Okay, so so let us use the constraint to express dxj, for example, in terms of other dxi, was I not equal to j. Now, how do we do that? We can say that I will write this dxj is equal to sum over I is equal to 1 to n, and of course I don't have j in this summation, so let me add this remark: I is not equal to j, and del g by del xi divided by del g by del xj. Of course, I am assuming that g depends on xj, otherwise we cannot do this, into dxi. So this look at this carefully. So I have this equation. So I am writing j terms separately and all other terms together. And of course, since I am taking on the other side, there will be a negative sign here. Okay. So this is what I will write dxj in terms of this, and then I will so go back to this expression of f. So let us write df is equal to 0 as follows. That is, sum over I is equal to 1 to n, I not equal to j, dou f by dou xi into dxi, plus dou f by dou xj into dxj is equal to 0. I am splitting this one thing separately. Now you can see that this dxj, I can write it from this equation. So use this equation. So from here I will bring this dxj and substitute it here. So then I have the following equation: sum over I is equal to 1 to n, I not equal to j, dou f by dou xi into dxi. Remember, there is no summation here, but because of this summation, you will have a minus sign, and sum over I is equal to 1 to n, I not equal to j. You can see the summation is same as the summation here, and dou f by dou xj, and this dxj, now I am going to write it as dou g by dou xi divided by dou g by dou xj into dxi is equal to 0. Now you can see that this summation is running on the index I, and I is not equal to j. So that means this quantity which I have here, that is dou f by dou xj into dou g by dou xj. So this quantity is not going to depend on the summation index because this is with respect to j and I is not equal to j. So I'm going to call this quantity as some constant. If I call this quantity as some constant, so let's call dou f by dou xj divided by dou g by dou xj. Let's call this as some lambda, a constant. We do not know what this constant is, and let's say that it is to be determined. Now, the moment I put this as a constant, recognize that this equation is very simple because you look at the summation is same, indexes are same. So I can write this equation as sum over I is equal to 1 to n, I not equal to j, del f by del xi minus lambda times del g by del xi into dxi is equal to 0. Now, note that this dxi, I is equal to 1 to n and I not equal to j. There are no n such elements here, only n minus 1 such elements are there because dxj is not there in this. And they are linearly independent. So if they are linearly independent, then the coefficients have to be equal to 0. So this implies dou f by dou xi minus lambda times dou g by dou xi is equal to 0 for all I equal to 1 to n and I not equal to j. So this is what we have from this equation. But now look at the definition of lambda. So from the definition of lambda, we have, so you take this on this side and then we have dou f by dou xj minus lambda times dou g by dou xj is equal to 0. So the definition of lambda says even with respect to xj, we have the same equation. That means this equation is, we don't have to now worry about this condition. This condition is not required. So by definition, the lambda, it also satisfies a similar equation. So you have, so if you have a constraint, so instead of so you have to extremize f of x1 comma x2 etc xn subject to a constraint namely g of x1 comma x2 etc xn is equal to 0 implies we have to solve a set of n equations given by dou f by dou xi minus lambda times dou g by dou xi is equal to, okay, and this lambda, which is something which we do not know at this moment, this is a method due to Lagrange. It's called Lagrange undetermined multiplier. Undetermined multiplier. And this method is called Lagrange undetermined multiplier. Now, how to find this lambda? We will come to. So, okay, let me say that once you get the solution, okay, so once we get x1 star, obviously this will be a function of lambda. Now, x2 star, this will be a function of lambda, and so on. From xn star, this also will be a function of lambda. And once you get this result, substitute this in the constant, namely g of x1 star of lambda, etc., xn star of lambda is equal to 0 to get to determine lambda. So this is the procedure how to determine this lambda. Now let me just add the last point. That is, if you have, let's say that you have more than one constraint, that means we have to extremize f of x1, x2, etc., xn, subject to not one constraint, but let's say there are many constraints. So let's say there is a function called g1 of x1 to xn is equal to 0, g2 of x1 to xn is equal to 0, etc. Let's say you have some k such constraints, gk of x1 and is equal. So the idea is same. So you are going to have for each constraint one undetermined multiplier. Okay? So you are going to so the prescription is that we have to solve. And remember, in each case, your solution at the point where the function becomes extremum is different because constraint will modify that one. So you have to solve an equation like this: is dou f by xi minus, so lambda 1 times dou g1 by dou xi minus lambda 2 times dou g2 by dou xi minus etc. minus lambda k times 2gk by dou xi is equal to 0, and for all I running from 1 to n. So that means these are n equations that you have to solve to get the extremum point. So this is something which you can write it in a shorthand notation like this: xi minus sum over j is equal to 1 to k lambda j dou Gj divided by xi is equal to. So this is the expression for constrained extremization condition that gives you an extremum point subjected to these many constraints. Okay, so this is called method of. So I think context books we call this as method of Lagrange undetermined multiplier. You might have seen when you want to solve some problems in classical mechanics involving non-holonomic constraints, you might have used this method. But essentially, this is the mathematical technique. So I try to give you the detailed technique. So whatever I have written in red, or whatever this color, more than family. So this is actually the mathematical technique. Okay, so now we are ready to do this problem of introducing extremization. Okay, so let us go back to our problem. So we have to uh, maximize this W. Now this W is a function of N1, N2, etc. These are like variables subjected to constraints. Subject to constraints. One constraint is that sum over j nj minus n is equal to 0. This is one constraint equation. And the second constraint equation is sum over j nj ej minus nu is equal to. So these are the two constraint equations that we have. So we have to extremize this subject to these constraints. Now, to do this problem, we recognize that this is one trick we always do in statistical mechanics. So recognize that logarithm of x is a monotonically increasing function. Monotonically increasing function. Okay. What is the use of this one? Okay, so let us say logarithm of some f. Okay, logarithm. Since it is monotonically increasing, extremum or extrema of f are same as extrema of logarithm. Extrema of logarithm. So if there is some maximum for f, for logarithm of f also, at the same location there will be a maximum. Because it is not going to, it is monotonically increasing. If it is increasing, it is increasing. If it is decreasing, it is decreasing. Correct? So you have this advantage. So if you want to find out the extremum of f, if for example mathematically finding the extremum of logarithm of f is easier, then you go ahead and do that because the extrema are going to be the same. So we are going to, and in statistical mechanics, we many times use this. So please keep this in mind that this as a trick, we use it again and again. So what we will do, see here why we are interested in logarithm, because this, remember this W of this N1, N2, etc. is a function like this, factorial n divided by product over j and factorial nj, right? So I maximizing this is a little cumbersome. So what we can do is we can try and recognize that this n and all these small n's, they are very large numbers. So we can write down logarithm of w, which is equal to logarithm of factorial n minus this product will become sum over j logarithm of factorial. Further, since some race coming from the, further, since this small n and this nj are all large, we can use what is called Stirling subtraction. Uh, do you also see this some line appearing?
Yes, sir.
I really don't know from where this line is appearing.
I can
It
change the
definitely.
surface of your graphic tablet.
Huh?
You may change the surface of your graphic tablet, whole surface.
Oh, okay. Okay, I think I have a problem here. I do not know. Can I just close it and open again?
You may
Yes, sir.
I mean, I will close this OneNote and then open again. Then maybe this problem will go. Succeeded in getting rid of this. Let's try to proceed and see how much it can disturb us. So we are going to have, we are going to write this Stirling's approximation. So this logarithm of W is going to be equal to n logarithm of n and of course minus n will be there, and here also I will have a term like that, so that will cancel. So let me not write sum over j nj logarithm of nj. Okay, this is what will be logarithm of w with respect to our Billings approximation. Now I want to use this Lagrange multipliers. So the idea is something like this. Let's say that I have dou by dou n, if I have some particular, let me call it as L of logarithm of w minus, let's say alpha is one uh, Lagrange multiplier. So dou by dou n L of, the first constraint is sum over j nj minus n. This is the first constraint. And let's say I have another constraint, so let's call this beta. Right now I do not, beta is a constant which is an undetermined multiplier. The next constraint is sum over j nj ej minus nu. This is equal to 0. I am just using the alpha and beta. So alpha and beta are Lagrange multipliers. I think this ray is trying to determine the slope of my hand movement every time. So alpha and beta are Lagrange multipliers. So this is, you can note that when I do this, this term will, so this term is not going to contribute anything, and this term is going to give you, the first thing is, let's write sum over a L n j by L n L into logarithm of nj plus nj into 1 by nj into del nj by del nj. That is as far as this term is concerned. Minus alpha times sum over j del nj by del nl minus beta sum over j ej into del nj by del n. Now you can see that this quantity is actually delta I, sorry, delta j. Okay, that means in this summation only j is equal to L term will survive. So this implies this one will, there is a minus sign here because logarithm of is also a minus sign here. So you have minus logarithm of nl. Here this will cancel away and you will have simply minus 1. Minus alpha, this is delta JL, so simply it is 1. So alpha into 1 minus beta into, you have EL equal to 0. So this gave us so suppose if I take this logarithm of L on the other side, okay, so you have, write down this NL is equal to e to the minus alpha minus 1 minus beta times EL. Okay, so this is your mm, NL. What is this NL? This is basically the equilibrium or the most probable value of the mode. But alpha and beta we do not know. We have to determine them. So that that part we have to do it by substituting this in the constraints. So let us look at the first constraint. We know that sum over j nj is equal to n. This implies sum over j. So let this alpha and this one is not going to depend on the summation index. So let me write it as minus e to the power alpha plus 1 into e to the power minus beta ej, okay, e to the minus beta ej, this is equal to n. This implies instead of determining alpha, I can actually determine e to the minus alpha plus 1 is equal to this n divided by sum over j e to the minus beta. So you can see I have determined this one. So if I have determined this one, then I have my nj. So nj is equal to n e to the minus beta ej divided by sum over j into e to the minus beta ej. Okay. Remember at this point we do not know beta. So beta is still undetermined. Beta is still undetermined. So we'll look at the second constraint equation. The second constraint equation is sum over a nj into ej is equal to this n into u. This is my second constraint equation. This implies, now I know what is this nj, so that is equal to, so let us pull this n and then put this summation over j ej into nj. Nj is, I have pulled this n, so e to the minus beta ej divided by, we'll have to now put some other index, let's say k e to the minus beta ej. This is equal to n into u. Now this n can get cancelled, and what we have is u is equal to sum over a ej into this quantity, I mean this quantity which is like probability of ej. Okay, this is the average energy, right? This is the average energy provided beta is equal to 1 by kb. So by requiring this quantity to be average energy, which is in thermodynamics is U, we are able to identify that this second undetermined multiplier beta to be equal to 1 by kb. So this tells us that whatever canonical probability density that we have obtained earlier is the most probable density of the most most probable mode. That means for which you have the number of ways in which it can be realized is the maximum. So this implies that the probability. So you can define probability or you call this as canonical probability can be written as whatever is this nj. Okay, so I think we wanted to call this as star, right? So let's call this as nj star. Okay, so it is given by nj star divided by n. Okay, so you can see from here that nj star divided by n is sum over a into eta minus beta e. So whatever is there in the denominator is what we called as partition function into eta minus beta e. So we are back to our mantra that this is our canonical probability density, which can be obtained by using a general most probable mode, which maximizes the number of ways that mode can be realized. So this is one way of obtaining this result, and this is a general result as far as the canonical ensemble is concerned. Of course, there is also one more general result, which is this is called method of most probable distribution, and we will talk about another method in probably another class. Now let us look at some applications. Okay, so let's first look at one of the application. Okay, so in the last class we talked about ideal gas, and we talked about ultra-relativistic ideal gas. So let us say that in this class we will look at the specific crystalline solids that we have discussed. So classical set of harmonic oscillators. So first let us look at classical oscillators. So this the Hamiltonian of the system is given by sum over I is equal to 1 to 3n pi square by 2m plus half m omega square pi square. So you can see that the partition function can be written as 1 over h power 3n into integral dq bar dp bar. As I told you, that one of the advantage here is that the integral is not constrained, into e to the power minus beta of h of q bar. Now this can be written as 1 over h to the 3n into integral over dq, and q can go from minus infinity to plus infinity, e to the minus beta half m omega square q square into integral minus infinity to plus infinity dp e to the minus beta q square by 2m. Okay, so this is for one coordinate, and I can evaluate this integral and then take this whole thing raised to the power 3n. And there are 3n q's and 3n p's. And luckily, these are just Gaussian integrals, so it is straightforward to do this integration. So this is 1 by h power 3n, and this integral is so square root of 2 by eta m omega square into pi, that is root pi. Okay. And this integral is square root of 2m by beta into whole thing raised to the power 3. So you can see that this m will cancel from here. So we have 1 over h power 3n and 2 pi divided by beta, beta into beta, beta square, so beta into omega raised to the power 3. Okay, so you can see that this is, you write this as 2 pi divided by h, or you write this as 2 pi kbt, because beta is there in the denominator, into h omega raised to the power 3n. Now this is actually equal to kbt divided by h cross omega raised to the power 3. Because I can bring this 2 pi down, and h by 2 pi I write it as h cross omega. This is like the quanta of the system. And now you can compare what we had obtained, the number of microstates in the previous case. If you have total energy E, we had E by h cross omega. Now you have kBt by h cross omega as your partition. Now, if you want to, I still can keep this as the partition function to be 1 by beta h cross omega raised to the power 3n. For reasons that will become very clear, because I am interested in finding out the internal energy, which is written as minus del by del beta r. So I'm going to use one of the relations that we derived. So that's equal to minus del by del beta of, I can write this as 3n, there is a minus sign, 3n logarithm of beta minus 3n logarithm of h cross 1. I can write it like this, and this is a partial derivation with respect to beta, so this is not going to contribute. So you have 3n by beta, or this is 3n ab, and this is the average energy which we have obtained in the previous case also. And you want to calculate specific heat, which is nothing but U by T, which gives you 3n AB, and you write this n as 3 times Avogadro number times the number of moles into kb, and ask what is specific heat per mole. That is given by 3 times R, and this is your, what is called, Dula. So whatever Boltzmann's calculation that we did earlier, it is much simpler to do this calculation, because what is involved is just the Gaussian intervals. Okay, so this is a set of classical oscillators. Now one can think of doing this, continuing this with a collection of quantum oscillators. So a collection of quantum oscillators. As I told you in the beginning, when we have this recipe, so here we have the Hamiltonian, and because this is a quantum oscillator, we have to solve this h psi n is equal to En psi n, and let's assume that this has been done in quantum mechanics, and I want only the input that I have n plus half. These are my energy eigenvalues. Okay, so these are the energy eigenvalues for one oscillator. Okay, for one oscillator. So I can now write down the partition function for one oscillator as sum over this n can go from 0 to infinity e to the power minus beta en. Okay, so this is essentially, I will have this e to the power minus beta h cross omega by 2. This is the energy corresponding to the 0-point energy. And then I have n is equal to 0 to infinity. E to the minus, I'm going to write this in the following fashion: minus beta h cross omega and raise it to power n. So n can go from 0 to infinity. Now look at this term that h cross omega by kbt. Now kbt is in general bigger number. So h cross, so this is definitely a positive number. Okay, this is definitely a positive number. That implies e to the power minus h cross omega by kp is something that is less than 1. Now, you look at this series. This series is a geometric series. So if you are going to call this x is equal to e to the minus beta h cross omega, then this series is 1 plus x square, etc. This is called a geometric series. Now I want to know what is this sum. So I do not know. Let's call this as S. Now I can write this S as 1 plus x into S, because if I pull out x, it will be again S. So this is nothing but, I take this to the other side. So 1 minus x is equal to 1. That implies S is equal to 1 by 1 minus x. So this series will converge to this function um, if suppose the modulus of this value x is less than 1. And we have already argued that this x is less than 1, and hence this series will converge. So I have e to the minus beta h cross omega by 2 into 1 by 1 minus e to the minus beta h cross omega. So this is my partition function for one oscillator. This for one oscillator. So you can see this quantum mechanical energy levels. Once you have, you can obtain this partition function, and once you get the partition function, then you have your total partition function. Z can be written as Z1 raised to the power 3. Okay, so this is so now we have this expression. I can, so which is equal to e to the minus beta into 3n h bar omega by 2 divided by 1 minus e to the minus beta bar omega raised to the power 3. Okay, so I will leave this algebra for you. So find u, which is equal to minus dou by dou beta of logarithm of z, and then find Cv, which is equal to dou u by dou t, and then take this limit that h cross omega by kbt is much greater than 1, and then get Einstein's specific equilibrium. Now, just to get practice, this is not the only way in which you can get. For example, you could have tried this. That is, you take Helmholtz free energy as minus kBT logarithm of z, and then obtain S as minus partial derivative of f with respect to t, and obtain U as f plus t. Because you know S, you know F, so you can obtain this, and then get your CV as. So this is another way in which you can get the same result as Einstein. So actually, I am trying to show both in the last class and this class the same problems that we have done using microcanonical ensemble, how to do them using canonical. But we will also do some applications mm, which are more easy to do in canonical ensemble and which cannot be done easily in microcanonical ensemble. Okay, so this is just to uh, show you that how we get the same results even if we take. Okay, so I will stop here, and I do not know. There is some inconvenience towards the end. Maybe from the beginning, with respect to this cursor showing that was disturbing, but I somehow managed to complete. You have to worry about why this is happening. Okay, any questions? Are there some questions? Has it been put in chat? I don't usually keep chat, or I will not. I will not get this chart when I'm presenting. I don't have any questions in the chat.